Maybe I could do this on my laptop. So this is R to the n. Okay? I'm using the here. Now, if A is positive junctional, we could rotate the coordinate system and rescale everything so that the coordinates lie in unit sphere. And substitute with the parameterization of things that lie on spheres, such as this, and then solve and apply the inverse mapping. But of course, this gets very complicated very quickly. Often it's not even possible to parameterize constraints this way. You have polynomial constraints. You can't simply find parameters such as the polynomial subset. So in some cases it's inconvenient, in other cases it's essential not to do it this way. Okay, I'm not sure, is this going to make sense continuing this version? I'm not sure I'm running it on laptop. It's okay? It's okay, alright. I'll just explain this is R2. In the break I'll switch to the I guess the more recent version of R. Okay, so suppose you want to minimize some function f subject to some constraint in red. And the constraint I've drawn here, and x is an R2, so you can see it on the plane. Okay. Now suppose you think that this point here is a possible solution. Okay, fine. Well, let's look at the gradient of f. That's the gradient of f. That is increasing this way. Gradient of c happens to be in this direction, let's say. It could be in the opposite direction. I haven't told you in which way c increases, but let's suppose for now that it's in this way. That means that I could actually decrease f by moving in that direction a little bit, without coming off this in a straight line. So whenever the gradient of f is not parallel to the gradient of c, I can always improve the solution by moving along the constraint. That means that I must have, at the solution, the gradient of f is proportional to the gradient of c. Okay? So, this is going to be tough. You know when it's telling me. Okay. At the optimum, we must have the gradient of f proportional to the gradient of c. Namely, this is true. And so, the gradient of Lagrangian, which this box means is defined to be equal to the gradient of this function. So what's happened is interesting, actually, because right here, this gradient does not vanish. At the solution, the gradient does not vanish. This gradient doesn't vanish. And yet we found something whose gradient does vanish. And it's much easier to solve for something whose gradient vanishes without having to think about it. So has everybody following this? Despite the boxes, box rendering. Okay, now suppose you've got multiple equality constraints. You're solving an optimization problem and you have to have these equality constraints hold for all points in the solution. And I'm going to allow n of these constraints. Then each constraint has its own gradient, so the directness increasing fastest. And suppose S is a subspace stand by these gradients, and that would be our orthogonal complement of the subspace. And suppose that at some point these constraints hold, and the component of the gradient in the orthogonal complement is not zero. That means that I can move just in the orthogonal complement, which means not moving along not changing the constraint at all, and can increase or decrease f. Its gradient in that direction is not zero. So that must mean that when I have multiple equality constraints, the component of the gradient of f orthogonal to constraints in the space orthogonal to constraints is zero. And that must mean that the gradient of f is expressible as in terms of the gradients of all the constraints at the solution. And these lambdas are called the ground multipliers. And in fact, again, this is identically equal to, or this is defined here. So I'm defining something called Lagrangian. So my original function I'm trying to minimize, minus or plus, doesn't matter. I'm just going to different signs for different lambdas. Some of these lambdas. So now as we go through these talks, I'm going to be throwing puzzles out at you now and then. And I'm color coding the puzzles. And I hope how I can do this one. Puzzles are in green. I'm not going to answer them as I speak. They're just sort of questions. They may be some very fuzzy questions that really close to my heart. For example, here, well, I just went from one equality constraint to many. So why didn't I go from one Lagrangian to many Lagrangians? Okay. Now things get a little bit trickier, but not much. if you have inequality constraints. So now we've changed the problem a little bit. Okay, actually, yes, okay. So we want to find the x, and x OK star will mean the solution. That minimizes this function subject to this constraint. It's one constraint, and now it's an inequality constraint. So what's new here? What's new is, at the solution, this constraint may actually be strictly held. And that means that I could actually, at that solution, remove this constraint as constraint, and the solution is still be a solution, because it's a solution starting. So one sort of brain dead but not guaranteed way to proceed here is just to blindly minimize this function, and then check that at the solution, the constraint is satisfied. And actually, that's quite a useful trick. But obviously, if it doesn't work, we have to work a little bit harder. Okay, so now what's happening here? So now my gradient of f is the same as before. And let's suppose that I'm at the solution. The gradient of c is this way. Now, the key point of this slide is that sign matters. The sign matters because I can go anywhere in this region and satisfy this constraint here. But I cannot go in this region. So that means that if I'm at this point and I'm at the solution, it must be that the gradient of f is proportional to the constant proportionality, the negative gradient of c, if I minimize it. So that means now I'm going to apply this to Lagrangian, f plus lambda c. Now signs matter. I have to have a plus here, because this is definitely minus. Gradient has to vanish, and the thing in red, lambda is positive. So if I'm minimizing a function subject to inequality constraints less than or equal to, then my Lagrangian has a plus lambda and a lambda positive. Of course, if I'm maximizing, then you can see the same thing with lambda negative. It works whatever combination you like to choose. Okay, what about multiple inequality constraints? So now I have exactly the same argument. It follows very close, so I won't go through it. But I wind up with a Lagrangian, which is just the sum of my effective function I try to minimize, and the positive sum of these constraints, and the gradient of that must vanish, except every one of these lambdas must be positive. Now suppose that at the solution, the complete solution, this the J constraint is strictly held, it's held strictly. Then removing this constraint from the problem makes no difference if you start at that solution or if you stay at that solution, because the constraint's not doing it. So that means that you can drop this gradient from this sum, okay, in that case, whether or not the gradient is 0, because the constraint doesn't matter. And that's equivalent to setting lambda 0 for that constraint. So, in fact, there's a case where if the gradient of f is actually 0 at that point itself, then you could leave this in, if the gradient of c is 0. But in most cases, you actually have to set lambda equal to 0, so that the gradient of the constraint you don't want is not in the sum. And in all cases, you can, if this constraint is not strict, you can set lambda equal to 0, for the reason I just explained. So you can always impose this product. Because for inequality constraints, either the constraint is strict and it's equal to 0, or its corresponding Lagrange multiplier is 0. And actually, this is sometimes sufficient to solve the problem just by inspection. It's a very useful thing. And at the end of the fourth lecture, we'll see it return as important solution to Entropy conditions, or one of those conditions. Right now, I just want to show you how it comes to this basic optimization theory. Okay? So now let's do some very simple examples. I'll have to just explain what this box is actually not too much. Okay. I'd like to streamline the distance between points on the n sphere. Well, obviously, for a one sphere, which is a circle, it's obvious, they're either antipodal or on top of each other. But maybe for n equals 73, it's not obvious. You know, who knows? How do I choose strength? So we're going to do it for arbitrary dimensions. And what we're going to do is embed in calligraphic R to the n plus 1. So you could be in space n plus 1 space. We'd like to extremize the distance between the points, subject to the fact that they both live on this sphere, which means that my first constraint, which is an inequality constraint, is that x1 lives on the sphere, that's what this says, and also x2 lives on the sphere. So now the Lagrangian is a function of two n plus 1 variables, x1 and x2, and here's the vector function I'm trying to analyze. Those are my constraints, so that's called the Lagrangian, which is what multiplies. And this is what it is if you plug everything in. So taking the gradient with respect to the little x1s gives you this equation, doing the same with the x2s gives you this, and this gives you the solution, which is namely that they're proportional. So either they're sitting right on top of each other, or there are opposite points, antipodal points in the sphere. But I just want to make a couple of points, or one point here. We've arrived at this equation, right? But it's not sufficient to solve the problem, because I could actually choose some corresponding, suppose I choose lambda as 9 here, and then choose the corresponding lambda here. Then both of these equations satisfy, but it's not a solution to the problem. So take-home message is you have to check that the constraints are still satisfied. This gives you a necessary condition for the solution, but it's not sufficient. Okay, so if x1 equals x2 here, then the gradient of f, the vector factor actually is 0. And so, as I was saying before, if the gradient of f is 0, the constraint itself, when x1 equals x2, does not have 0 gradient, because this is not a 0 gradient anywhere, which means the lambda must vanish. So for the case where these two points are sitting right on top of each other, the lambda vanishes for the reasons I just explained in this slide. Okay, let's do a rather simple example. This is one that most kids know the solution to, but they don't know why it's the solution. So we're going to prove in one line of the Lagrange multipliers what the solution to this is. And this is the plot we're looking at. We're given a parallelogram, the sidelengths you can choose, but with rivers to see is fixed. And what shape has the largest equilibrium? So it has height h in base b, and given that I've been given this parallelogram, I can always tip it up, let me stop from doing that. I know that increases the area, so I'll always tip things up. So in fact, I don't have to deal with spheres, and with squares, rectangles. So this is a rectangle. So now I want to maximize base times height subject to the perimeter being constant. The Lagrangian is this. Vector function minus lambda times this constraint. The gradient of the Lagrangian vanishes, even though the gradient of each of these is not, which tells me the basic result. So 1 line, or 2 lines through. One of the things I want to point out in this example is, I didn't actually have to compute what lambda was, ever. It's a sort of mysterious thing. I've got these lambdas floating around. I use them to formulate the problem and put them in a certain perspective. But often I don't have to find out what they are to get the solution. And here I do. I didn't tell you what lambda was. I could plug it in and tell you that. But I didn't need to figure it out. So this is sometimes called the method of undetermined multipliers. Okay, so now some very simple exercises for you folks in green. This is not to do now, but we're going to describe it some other time. What coefficients maximize the convex sum of fixed numbers? I give you 10 numbers. They're of arbitrary sign. The convex sum means I give you 10 coefficients, which sum to 1 and are positive. And I want you to tell me what those coefficients have to be to get that to be maximized. Number 2 is minimize the sum of squares subject to the constraint that sum of the x's is 1. And number 3 is maximize the sum of squares subject to this constraint. Obviously, if you stop there, you can just make it as big as you like. So let's also make this positive. Choose x negative and make this as large as that. Okay, and here's a case where each of these KPT conditions gives you an answer very quickly. Just knowing that that must be true of the solution. And the constraint is just x sign. Okay, slightly more sophisticated solution, actually three slightly more sophisticated puzzles. This crops up all over the place. They crop up in signal processing, where you have net Reichstrom sending a certain number of bits down a pipe, and you are given a certain amount of distortion. But I'll actually describe it with a factory model. But it's everywhere. It's particular. Using the graph multipliers. So imagine you have some number of widgets you want to manufacture, n widgets, and you've got here 4 factories making widgets, but they make them at different costs because some are expensive places to live and some are cheap places to live and so forth. So that the plot of the cost to make a widget versus the number of widgets is different for each factor, which is what these different colored lines are. And I want to make 1 million, exactly 1 million. So I know people don't buy 1 million of these things. but I want to minimize the total cost to do this. And for factory I, produce ni ridges across ci ni. So it's just some function, I don't know what it is. It could be horrible, non-convex, who knows. Actually, here it's nice. It doesn't have to be that nice. So the problem we'd like to do is to minimize this sum of costs subject to the total number of ridges being constant, which here amounts to saying either I give you a fixed number of bits I want to send down the fiber, what's the best distortion you can realize of these different fiber systems in order to work over them, or the converse of that. I'll give you a fixed error rate on the rate, how many bits can you send out. Well, actually, we can say something very interesting right off the bat using the Lagrange multiplier. The Lagrangian here is just the vector function, as before, plus, because it's equalities, lambda my Lagrange multiplier times the constraint, n must equal this, so this is equal to 0. Should be equal to 0. And then taking the gradient of this gives me simply that the derivative of my costs with respect to my number of widgets at each factory must be the same. So wherever I am, the operating point on these curves, it must be such that the slope on at each point is the same. But that makes the problem really easy to solve now, because I can choose a point, say this one here, then I can find the point that has the same slope on each of these other curves, and I can gradually slide up these curves, keeping the slopes the same. So I only have now a one-dimensional thing I have to solve. So it's apparently, again, it's not solved the problem for you, but it's framed it in a way that makes it really easy to understand, easy to approach. Okay, now for a problem that was around 50 years before Lagrange. I believe that the Louis brothers had a couple of hours. And Lagrange solved it in his living years as an application. I'm going to introduce something, and a couple of new ideas here. This is a variational problem. So we're going to do a little bit of variational calculus in one slide. It's called the isoperimetric problem. And the problem is to find the curve of fixed length, rho, and fixed endpoints that enclose maximum area. So think you've got a piece of string here. You want to arrange the piece of string to have maximum area under it between this line and the string. So the area under, I'm going to parameterize this string with a function y. And the area is this, and the length of the string is this, where y prime means y by dx. So my Lagrangian now is this. Here's my vector function. Don't worry about integrals, we're not afraid of integrals. Minus lambda times inequality constraint. So what's new here? What's new here is I have some integrals floating around. That's fine. Don't worry about that. The other thing that's new is it's not a variable I'm trying to find, it's a function. I'm trying to find a function of y that gives me this maximum. So that's something new. So just to tie in with Lagrange, it turns out Lagrange was the person who introduced this notation delta to mean a variation of the function in 1755. So what I'm going to do is I'm going to vary this function a little bit, and I'm going to denote that variation by delta y in such a way that the variation at the beginning and the end vanishes. So these points are fixed. Every function winds up in the same place and starts in the same place. But in between, y is arbitrary, but it's a smooth curve. So then I get this, where I've got this variation. Now variations behave just like derivatives, because it's a small change. So it turns out that this is equal to this. And now I've got my delta y outside. And that's the key trick. Now that I've got my delta y outside, since delta y is arbitrary, and since this vanishes, everything in this black bracket is vanished. Because I can choose a delta y that's 0 everywhere at such a point. So what does that tell me? That tells me that this quantity here has vanished, which means that 1 minus lambda kappa, where kappa is defined to be the curvature of this curve, vanishes. So what we found in the few lines using the multipliers is that the only surface that satisfies this is a circle, an arc of a circle or a straight line. Constant curvature. Okay. Do something slightly closer to home. I'm going to ask you this following question. I give you a univariate distribution, and I want to know which one has maximum entropy, maximum uncertainty. So, what is the entropy? Well, here I'm using differential entropy, but it's essentially, this is a distribution, so its sum is 1, it's positive. I'm going to fix the mean, this is the mean. I'm going to fix the variance. Actually, this isn't exactly right, so I'll subtract the mean, but I'm going to fix these modes. And I want to minimize this product subject to these constraints. So I'm going to find that distribution that has minimum, maximum entropy. And there's a kind of shorthand that you can use when you do functional analysis, which is to use functional derivative, which is, all it does is encapsulate what I showed you in the last slide, is to say that a small variation in one function with respect to another function gives you this delta function, which, when integrated, pulls out, well, let me just go on. I hope you've seen this delta function before. It's just 1 at when x equals 1, 0 everywhere else, so that it integrates to 1. So the Lagrangian now takes this form, and imposing that it be 0 with respect to arbitrary variations in this function f, and then integrating with respect to x, which this allows you to do, gives you this, which says that it must be a Gaussian. So we just discovered in one slide which we found multiplied, so the Gaussian is the univariate distribution of maximum entropy if you fix the mean and the variance. So here's some more puzzle. Isn't it a uniform distribution that has maximum entropy? So what's that about? And what do you get if you fix the mean and not the variance? Do the same thing. And what distribution do you get if you fix only its support? So now I give you a function. I say it's 0 outside of the 0, 1 interval, and whatever you like inside. What distribution there maximizes it? Okay. So this is the last slide on the branch multipliers. This is actually a direct machine learning application. So now, let's suppose you have a discrete distribution, hereby, where the I is sum to 1, so this is just a distribution here. But now you have some non-linear constraints on your distribution. So the non-linear constraints, just imagine you're doing document categorization, and you know that documents about baseball in America twice as likely to occur as documents about soccer, which are 10 times as likely than documents about neutron stars. And you want to encode these probabilities with a bunch of linear constraints like this. But you want to say, I'm maximally uncertain about the rest of the universe. I don't know anything else about this distribution. So I want to find that distribution which satisfies this constraint, but is otherwise maximally uncertain. In other words, otherwise has maximum entropy, subject to these constraints. So here I go. Here's the effective function. Here are my constraints. This is the constraint. The interesting one is just that there's some 1, and that the p is positive. And if you plug in and just say, okay, I'm going to vary p to vary l, and that relation must vanish, then you get this, which is logistic regression, actually, where the parameters now are these values, those things you didn't know. And this is also, you can argue that this is a multiple distribution. Okay, so that was a whirlwind tour on ground multipliers. So before we go on to functional analysis, any questions? Okay. Now, as I said, this next lecture is delaying the ground multipliers. So I'm not going to leave anything out. That's the idea. And my hope is that by the end of the lecture, no one here will fear Hilbert spaces or anything like that anymore. Okay. So it's a brief tour of Hilbert spaces, norms, and all that. So let me start with, oh, by the way, my slides here are different from the slides for you. I've improved this. And probably this just to point you at some good work. So the first one's the difference in Hilbert spaces is excellent. Yes, it's common bar, but this is, it's only quite just one, this is so it's on the very bottom of the food chain. What is the field? The field is 3 things. It's a set F, and the objects you like, and 2 operations, which we call plus and times. Such that on the plus, this set is abelian, with some identity equal to 0. And then if you take out the identity set, then on the times, it's abelian, just index yx, with another identity, and actually these identities come up with the same. And times is distributed over plus. So it's just a way of encapsulating what you mean by arithmetic on real numbers. But you don't have to have real numbers here. You have all sorts of different fields. And in fact, we'll have to use various kinds of fields in this form. So, just some examples. With plus getting addition in terms of the multiplication. For the reals, the field, the set is the real numbers. The rational is the set is the rational numbers, the mixed numbers. So you might ask, everyone understands me, it's always interesting to ask what's the smallest, what's the biggest, how many of them are there, like that. So what about fields? The smallest field. The smallest non-trivial field is a discrete field, Z2, contains two elements, 0 and 1, with plus meaning XOR, so that 1 plus 1 is 0, and times meaning and. So two puzzles here. The Z2, because it's very simple, you write down the multiplication and the addition table, and it's just 4 entries in each. Why can't you use OR? Why can't you use XOR? And the second puzzle is, for R plus, for positive numbers, is that a field under these conditions? So, how many fields are there? Well, of course, there are infinitely many fields. You can ZP, so modular arithmetic mod P where P is prime is a field. But you can define an ordering on some kinds of fields. So an ordering on the field is just like less than or equal to or greater than on the reals. And the real numbers and the rational numbers can be ordered, but the complex numbers and Z2 cannot be ordered. And in fact, no finite field can be ordered. For ordered fields, you can define a highest and lowest, or a supremum and infimum, roughly speaking. And an ordered field is more complete if every non-empty set, subset, has an upper bound. Any number that's not bound doesn't have to be close to a mile away. If it has an upper bound, it also has a supremum. This is not true of the rationals, but it is true of the reals. And so here's a key point. There's only one kind of field, actually, in the sense that if you require the field to be ordered, every complete ordered field is just the reals. It's just the real numbers. So, okay, I've got there's some other stuff. Vector space. Vector space builds on the field. People are using vector space throughout the brief. So what is a vector space? Just to be clear about what it is. Some set, again, can be anything you like, and a field, and these operations plus and times again, from the set, times the set into the set. So I can add elements to the set, okay, and I can multiply elements to the set by a scalar, such that all of these conditions hold. So we're abelian under addition, commutative under addition and multiplication, associative here, and distributive times distributive. It's a bit like field, but it's over two things now. It's elements to the set and elements to the field. And there's an identity element too. So a vector space generalizes the notion of vectors in Rn, and it's a huge generalization. Hilbert space is a vector space. Banach space is a vector space. Vector space is a vector space. So there's all sorts of things that are not irregular numbers for the vector spaces. We'll come across an example. Now the field that you choose when you define a vector space matters. When you see it, okay. This says that Rn over the field R has dimension n. What do I mean by dimension in the field? I mean the maximum number of linearly independent objects, actually in the vector space. Now, I know you all know what is meant by linearly independent. So this is Cn, complex numbers of n dimensions, over the field C has dimension n. The Cn of the reals has twice that dimension. Why is that? For a vector space, if the set you choose is C and the field you choose is C, then if you feel this is R, then 1 is an element of the vector space, and I, another element of the vector space, are linearly independent. But if this is C and this is C, they are not. So field is a critical component of the vector space. It really matters. So some more, a little bit more sophisticated examples of vector spaces. Functions themselves can be thought of as vector spaces if they're ranges of vector space. What's that mean? That means I have to be able to add two functions. What does that mean? Well, if I add two functions, I have to be able to tell you what value it takes at some point. So So it looks brain dead and trivial, but it's really not. I mean, I could define this to something else, but let's define it to this. So now I've told you how to add just functions, abstract functions, before you evaluate anything. And I've got the multiple functions, and you define it to do this. I just told you what happens whenever you evaluate it, that's what the multiplied function looks like. So there's a slightly more trivial version of vector space. Matrices, another one. Where the field is the complex numbers. And something called LP, for p greater than 1, which is the space, arguably the space of all infinite sequences of complex numbers, such that they converge. Well, that means that this sum is finite. What's going on? Why is that special? Well, okay, let's think about that. I add two elements of this space. So this X is actually a whole sequence. It's an infinite sequence, and it converges. And Y is another whole infinite sequence, and it converges. And I wonder what's it mean to add them together? It must mean that when I add them together, the sum converges, or it won't be in that space anymore. So I'm using the fact that if I have two sequences and they both converge, and I can add them turn by turn, and that also converges. Similarly, if I multiply a sequence by a number, and it converges, then I can take the multiplication of the sentence. So these operations make sense for these particular kinds of sequences. Okay. How about inner products? An inner product is really a huge generalization of the notion of a dot product in the Euclidean space. So now you've got a vector space over C or R, and you've got some function which we're going to denote by these angle brackets, which maps points, 2 points in your vector space into a single number, which for us is probably going to be R most of all, it could be complex numbers. So it's going to be an inner product if this is true. Inner products of vectors themselves are always positive. They only vanish if the X vanishes. And they're linear, actually, in both arguments, so we don't have to say that here. This is also a linearity constraint for all scalars. This bar means complex conjugate in the case where you have a complex field. If you've got a function that satisfies these conditions, it is an inner product no matter what it does. Okay? As long as it goes that those key things. So, examples of inner products. Well, the obvious ones. Vector space Rn over the reals with just the inner product defined by the dot product. L2 is a little bit more curious over the reals again. So this defined by pairwise multiplication over 2 sequences. So now I have a point in L2, which is a whole sequence, another point in L2, which is another whole sequence, multiplied together by term, that defines the inner product in L2. By the way, L2 was first funded by David Hilbert in his television product form. So it's sort of the precursor of Hilbert spaces. And in fact, we'll come back. L2 is a very special Hilbert space, and I'll come back at the end and say what a Hilbert space is and why it's special. But just to let you know now, it is a very special Hilbert space. Finally, vector spaces with matrices over the reals, all the complex numbers. Now I define an inner product just as a map to a number, so I can get the trace of the product of these things. Okay? It doesn't have to be a square matrix. You just have to make sure that it makes sense. Let's actually check that one in detail to make sure, let's go through these conditions and make sure it really is an inner product. Well, it's certainly true that the inner product of X with X is positive, because the trace of XX is just the sum of the columns mod squared, positive. And for the same reason, this vanishes only when X is 0. Okay? The trace is linear, so this is certainly true. Very nice. And the trace is also linear, so this is true for all scalars. And finally, this last one requires that you know that the trace, you can take the transfer of reverse two objects, so that's simple. Yes, I did. Yeah, there's an X transpose. Right. Yeah, the first thing is transpose. And actually, if you we'll go back to this later, but every inner product generates a norm, and in this case the norm it generates is called a Tübingen norm. We'll play with that a little bit on Friday. The inner product is a very general idea. And there's something that actually Bernard already used called the Cauchy-Schwarz inequality, which holds for any inner product. And it's this thing here. So, okay, you've seen this. It's like size, it only took the spaces of X, Y, cosine X squared, X squared, Y squared. This is true for any kind of product. But the fact that this is true for any kind of inner product means you can define an angle, as long as you can define another product. So suppose I have matrices. I can define an angle between matrices. And if I choose to do it this way, then the angle between these two matrices is simply 0.4 degrees. And in fact, this has been used, or something like this has been used, something called thermal alignment, where you are using the geometric properties of the inner product to describe how aligned or how lined up things are. Okay, I think I'll stop there. And we'll start with the constraint time. Okay, great, that's it.